So next topic is we need to cover look at the definition of bounded and unbounded set using the quantifiers, and then supremum infimum, and then completeness axiom on R, and some problems questions we will discuss based on these definitions. So before starting, let us recall some properties of real numbers. That real numbers are set of real numbers with respect to usual addition and multiplication. It basically forms field because every non-zero element has multiplicative inverse. Also we can do comparison between the members of between the real numbers. Why? Because it follows law of trichotomy. Given any two real numbers x and y, either x is equal to y, x is less than y, or y less than x. That is exactly one of the following is true. This is the reason why R with respect to its usual addition and multiplication it forms field, and with respect to this ordering, it is basically ordered field. Whereas set of complex number is a field but not ordered. We cannot compare two set of two complex number, that which one is bigger, which one is smaller. Now next is let us start from the definition of upper bound and lower bound. So first of all look at the definition, and then we will understand it with the help of examples. This one is the definition of upper and lower bounds. I am taking it from the book of Ajit Kumar and S. Kumaresan. Suppose A is some subset of R, because we are discussing real analysis. So here whatever subset we are choosing, either it is a real number or subset of real number. So suppose A is not non-empty and non-empty subset of R, we say that a real number alpha, it may or may not be subset of A. Alpha is coming from R, alpha is coming from set of real numbers, is an upper bound of A if for each x belonging to A we have x less than equal to alpha. So see, in terms of quantifiers, actually quantifiers are symbols or phrases used to quantify things, and it is used for precise writing in mathematics. So for example, for every is this is notation for every universal quantifier. For every there exists existential quantifier, there exist. This is the notation for belongs to. So we will use this. So as per in terms of quantifiers, if alpha is an upper bound of any set A, any non-empty set, then every member of the set for every x belonging to A, x has to be less than equal to alpha. So this is the definition of upper bound. For example, let us take, for the sake of explanation, A is equal to say 2, 3 and 4. Then I can say that alpha is equal to 5 is one of its upper bound. Why? Because every member of the set for every x belonging to A, x has to be less than equal to alpha. So just compare x for every member of the set, x has to be less than equal to alpha. So in place of alpha we are claiming 5, and member of the sets are 2, 3, 4. So one can see that 2 is less than equal to 5, 3 is less than equal to 5, 4 is less than equal to 5. So 5 is one of its upper bound. So if there exists at least one upper bound, then we say that the set is bounded above. The alpha equal to 4 is also one of its upper bound. Alpha is equal to 4. Alpha is equal to 4 is also its upper bound. Because every member of the set every member of the set is for every x belonging to A, x is less than equal to 4, 2 is less than equal to 4, 3 is less than equal to 4, 4 is less than equal to 4. So, one can see that the upper bound may or may not be member of the set. For example, here alpha equal to 5 is not member of the set, whereas alpha equal to 4 is member of the set. In fact, every real number greater than equal to 4 is its upper bound. So, set of all upper bounds for this set of all upper bounds of set A, I can write it as collection of all those x such that x is greater than equal to 4, or in interval form I can write it as 4 to infinity. So, all these are collection of upper bounds of the set A. Now, next definition, a real number alpha is not an upper bound. Next. Now, how to discard that a given real number is not its upper bound of a set? So, for this what we will do, I will use the same example. Let us look at the same example. Okay. A real number alpha, if it is given that a real number alpha is not an upper bound of a set, so we need to produce at least one element x belonging to A such that x exceeds alpha, For example, if I am claiming that alpha equal to 2.5 is not an upper bound of the set A consists of this 2, 3, 4. For the sake of convenience, I am starting from a finite set having just 3 elements. So, if it is not an upper bound, then from this set I need to produce at least one element. Say there exist 3 belonging to set A such that 3 exceeds alpha, that is 2.5. So, if I am able to produce at least one member from the set which exceeds this alpha, then 2.5 is not 2.5, the claim of upper bound is discarded. Similarly, 3.5 or 3 is not its upper bound. Why? Because there exists at least one element 4 which exceeds this 3. So, the smallest upper bound among all these upper bounds 4 to infinity, the smallest the least upper bound is called as supremum. So, we will look its detail, that supremum of a set is basically least upper bound, and in this particular case it is basically 4. So, the technique will be, first of all we need to look at upper bound, existence of at least one upper bound. If there exists at least one upper bound, we will say that the set is bounded above. Next step is to look at collection of all those upper bounds, just like we did in this case, we have done in this case. Look at collection of all those upper bounds, and from those upper bounds the least upper bound is called as supremum. Now, how to express it in terms of quantifiers? So, next definition, another geometrical interpretation for this is, if alpha is not an upper bound of A, then I need to produce at least one x which exceeds this alpha, x is greater than alpha. So, this one is the geometrically represented here. If alpha is an upper bound of A, another upper bound of A such that alpha dash is greater than alpha, then obviously since every member of the set A given by x, for every x belonging to A, already alpha is an upper bound. So, x is less than equal to alpha, so, and alpha is less than alpha dash. So, obviously x will be less than equal to alpha dash also. So, this is the reason, if alpha is one of the upper bound, so any member which is greater than alpha is also going to be its upper bound. Alpha dash is also an upper bound of the set. Similarly, one can define the lower bound, but here I am starting from upper bound. We will look at collection of all upper bounds, then its supremum, that is the least upper bound, and parallel we will develop parallel is the definition for lower bound. Then we will look at collection of all those lower bounds, and then infimum or greatest lower bound. Now definition 1.2.2. If A is a non-empty subset of R, it is said to be bounded above in R if there exists alpha belonging to R which is an upper bound of A. So if any set is bounded above, then there exists at least one upper bound. If there exists at least one upper bound, then we will say that the set is bounded above. The set is, so in terms of quantifiers, we say that any non-empty subset is bounded above if there exists at least one. There exists at least one means there exists at least one. There exists alpha belonging to R means there exists at least one. At least one. There exists at least one. So if it is given that a set is not bounded above in R, this means there exists no upper bound, no upper bound. So how to discard that? If for each alpha, given alpha is an upper bound, I need to produce at least one element from the set which exceeds this alpha. So in this way we will say that a given set is not bounded above. For example, n subset of R, though it will be proved using Archimedean property of R, but the set of natural number is not bounded above. Why? This set 1, 2, 3, 4 and so on, this is not bounded above. So using this definition, how we will discard that this set is not bounded above? Suppose I am claiming that alpha is equal to 100 is its upper bound, is its upper bound. So to discard this, I need to show that I need to produce at least one member from this set which exceeds this 100. So there exists x equal to say 101 belonging to set of natural number such that 101 exceeds 100. So this, in this way 100 is not its upper bound. So whenever a claim is given, whenever alpha any real number is given, say 100 or 100.5 or 100.3 or any other real number, and we need to show that this is not its upper bound, then I need to produce at least one member from the given set which exceeds this alpha. So this is the technique we will use to show that A is not bounded above in R. In terms of quantifiers, we say that a subset A of R is not bounded. Here this notation, remember, it is used for this one. I mean A may be equal to R, A may be proper subset of R. We are talking about non-empty set. So for every alpha belonging to R, there exists x belonging to A such that x exceeds alpha. So to discard that alpha is not an upper bound alpha, we need to produce that at least one member from the set which exceeds this alpha. So this is the technique we will use to discard that, and it will be used in various proof. Even in proving Archimedean property of R, we will look how to discard that this set is not bounded above. Similarly, just look at this property, we will come back to again. If A is non-empty finite subset of R, then upper bound of A, then there exists at least one upper bound of A which belongs to A. There may be more than one upper bound, but at least, for example, in this case we have shown that 2, 3, 4. In this case, there are several upper bound. There are in fact every real number greater than or equal to 4 is its upper bound, but alpha is equal to 4. One of the upper bound belongs to this set. Similarly, any lower bound of a non-empty subset A of R is less than or equal to an upper bound of A. Lower bound we will talk later on, parallel concept. Now this definition 1.2.4, A is non-empty subset of R is bounded above. If any non-empty subset is bounded above, then a real number alpha belonging to R is said to be its least upper bound. This is the definition of least upper bound. In some books you will find it as supremum. the first condition is alpha has to be an upper bound of A, and if there exists another upper bound, then, and we are calling alpha as the least upper bound, then alpha has to be less than equal to beta. So this is the definition of a least upper bound. For example, in this set A equal to set 2, 3, 4, 2, 3, 4, collection of all upper bounds, collection of all upper bounds is 4, and in fact every real number greater than equal to 4 is its upper bound. So least upper bound in this case, all these 4 and every real number greater than equal to 4 is its upper bound, but least upper bound LUB, least upper bound of this set A is 4. So among all upper bound, the least one is called as least upper bound. So this is the definition for least upper bound. A greatest, similarly in case of lower bound, one can first look at the lower bounds, then we will collect all those lower bounds, and the greatest lower bound is called as infimum. Here the terminology by some other authors will be used as infimum of the set. So there is a result. I am not going to right now its proof. Look at the statement of this result, that if A is a non-empty subset, bounded subset of R, and alpha beta are its least upper bounds, then it has to be unique. It has to be unique. Second result, a real number alpha is least upper bound of A if and only if alpha is an upper bound of A, and if beta is less than alpha, then beta is not an upper bound of A. So this logic we will use in doing the Archimedean property of R, because already alpha we have assumed as the least upper bound. So any real number less than alpha is not its upper bound. So how to discard this? So if beta is not an upper bound, then there must exist at least one element from the set which is going to exceed beta. For example, in the case of this 2, 3, 4, this 2, 3, 4, collection of all upper bound, is 4 to infinity. Now any real number less than 4, if beta is less than 4, then there exists at least one element which exceeds this beta. Say for example, if I choose beta is equal to 3.9 is less than 4, then there exists x equal to 4 which exceeds this beta, So that is what written here, that if beta is not an upper bound of a given set, then there exists at least one element from the set which exceeds that beta. Similarly, if we are claiming that alpha is its least upper bound, and beta, if we are subtracting any strictly positive real number epsilon from this alpha, then obviously beta will be less than alpha. This means beta is not going to be its upper bound. So there exists at least one x belonging to set which exceeds this beta, So this is another way of representing this. Now look at this example. A equal to 0, 1, open interval 0, 1, that is all the collection of all those x such that 0 is less than x is less than 1. Then we need to show that its least upper bound of this set is 1 and greatest lower bound of this set is 0. So what we will do, given this set A is equal to open interval 0, 1. So first of all, we will show that this set is bounded above. So alpha equal to 1 is one of its upper bound, because every member of this interval is because for every x belonging to A, x is less than equal to alpha, the 1. So 1 is its upper bound. Similarly, any real number greater than equal to 1 is its upper bound. And if we have at least one upper bound, then we will say that the set is bounded above. Now collection of all upper bound, set of all upper bound, set of all upper bounds, set of all upper bounds is 1 to infinity, 1 to infinity. Now among all these upper bound, which one is the least one? So least upper bound of this set open interval 0 1 is 1, least upper bound is 1. So this is what given here. Similarly, look at the set of all lower bound, set of all lower bound, that is if alpha is lower bound, the definition for lower bound is that if alpha is its lower bound, then every member for every x belonging to set x has to be greater than equal to alpha. So 0 is one of its lower bound. Why? Because every member in this open interval 0 1, every member is going to be right to 0, right to 0. So 0 is one of its upper bound, and every real number less than equal to 0, every real number less than equal to 0 is its lower bound. So collection of all lower bound, collection of all lower bounds, collection of all lower bounds, I can write it open interval minus infinity to 0, 0 closed at 0, and from this the greatest lower bound is 0. So that's what the greatest lower bound of set A is 0. This is the technique we will use in doing all these questions. Now, so if a set is bounded above, in R, then we have the least upper bound property, and as per this, see the least upper bound, the existence of such alpha, if a given set is bounded above, then from those collection of those set of all upper bounds, the least one is called its supremum or least upper bound. So for existence of least upper bound, the set has to be bounded above at least one upper bound. So this is the statement of least upper bound of R. The least upper bound property of R, given any non-empty subset of R which is bounded above in R, there exists at least one alpha such that alpha will be least upper bound of the set. So this is for non-empty and bounded subset of R. In fact, we can say that every non-empty and bounded subset of R will have least upper bound. Now, and if it is bounded below, it will have greatest lower bound, and if it is bounded above as well as bounded below, then the existence of least upper bound as well as greatest lower bound is by this property called completeness property of R, completeness property of R. Now remaining portion we will cover in the next lecture.